Good afternoon, everyone. So I'm Zhang, and I'm from University of Groningen. Today I'm going to talk about the active learning potential via Gaussian regression, focusing on the application to fracture in error. So it's actually the atomistic simulation of the crack tip response in ferromagnetic BCC error. So that's to be specific to the material. So as we all know that just get directly into the business, should skip the motivation. The fracture is a multi-scale phenomena, as we all know. And if we measure the fracture toughness at engineering scale, centimeters, we get the fracture toughness of, in the order of 10 to 100 kilojoule per meter square. If we measure it at macro scale, we get the fracture toughness in the order of 100 joule per meter square. So clearly that in this process, dislocation plasticity play an important role in dissipating energy at a larger scale. But it is not fully clear why this of this phenomena, and also since it's the fracture starts from the atomistic scale, so but most of the existing predictive theory for fracture are phenomenologic. So here we want to build up a predictive model for fracture using a bottom-up approach, which starts from atomistics. Okay, big part. Speaking about atomistics, so as I said before, the experiments are difficult and also expensive to conduct. I didn't find any experimental data on the where you have the TM images of the crack tip in ferromagnetic error. It's probably because of the magnetic state's influence. It's difficult to capture that by using the microscopic techniques. So here we use classical molecular dynamics in which the accuracy relies on the interatomic potential. The interatomic potential describes the interaction between the atoms in an atomistic simulation setup. So here we use this specimen, and the x direction is the crack propagation direction, y is the crack plane, and Z is the crack front. And these blue atoms are boundary atoms, so we apply the displacement solved by anisotropic linear elastic fracture mechanics to the boundary atoms and relax the system to let the system to evolve. So there already exists some classical molecular dynamics modeling of crack tip response. Here I show this is for the same crack system, but using different interatomic potentials. As we can see, we can observe cleavage, dislocation emission, and phase transformation. So this is this blue color is BCC, and this is HCP. So one might be confused because in principle, the different interatomic potential should predict the same behavior for the same crack system if these potentials converged, or that is to say they are reliable. But the fact is they don't. So they give the contradicting results, which means these potentials are not trustable enough. So one way to solve this is to use the quantum accurate method to model the crack system. But we can see that to model a crack system, at least the size of the system has to be has a radius of 15 nanometers, which is not possible for DFT to handle. And we have an alternative solution called the machine learning interatomic potential, in which we let the interatomic potential learn from the quantum data, and thus enable the prediction of fracture. So to construct such a machine learning potential, we need three essential steps. First, we need a quantum accurate database, which is the consistent set of DFT calculations normally. And then we extract this data by assumption of localization. So which means that the atom only interact with its neighbor atoms within a set cutoff radius, and then we can describe this atomic environment by different method. So it's an independent research field actually. So it's called the description, also the representation of the atomic environments. So once we can represent the local atomic environment, we can correspond it to the energy of this atom, and when we have the X as the atomic environment, Y as the energy, we can predict the structure, the energy of the structure, and then calculate the force and all related properties. So with this machine learning potential, we can reach near DFT accuracy. It can also handle large systems as 10 to the millions of atoms, but the limitation is it has limited transferability, which can be solved by adding more relevant data. So here we adapted a Gaussian approximation potential framework developed by Gábor, and in this Gaussian process regression, the X is the atomic environment, Y is the energy. So one can compute the covariance between this X, between the local atomic environment, to compare the similarity of the atomic environments, and then get the prediction of the new atomic environments. And the benefits of using Gaussian process is that it can not only predict the mean value, also the variance of the new data. This variance could serve as a error index, so it can quantify how much the potential is extrapolating. And with this method, we also adapt an existing database developed to study the thermodynamic properties of a ferromagnetic ion. We did a key test. So in the key test, we increase the stress intensity factor and calculate this variance. We call it predicted error. So we can see the error blows up with the increase of the K. And here is some snapshots during the simulation. We can see it predicts the scattering of atoms, which is not physical. So to enable the prediction of fracture, we enrich the database by adding more data. The first thing come to mind is that we can include some crack relevant database. Imagine if a crack wants to propagate, it involves that the separation of surfaces. Also, we calculate the strain field ahead of the crack tip to include the strain space of those atoms. There is a simple component analysis of the strain components of the old DB data. So this old data, this is from the existing database. This is DB9 is what we developed. This is from the linear elastic fractional mechanics. Because it's 2D, the planar strain or planar stress. So after the principal component analysis, it's some straight line in the principal space, and we can see that our data expand the boundary of the old data. But by adding this data, we did the key test, and we found that this is still not enough for GAP to predict fracture. So we developed the active learning algorithm to let the potential to learn the crack tip environment. In this algorithm, we first do a crack simulation. During the crack simulation, we detect the extrapolation by comparing the predicted error. We set a threshold for this error. If the error of any atoms goes beyond this preset threshold, we stop the simulation, take out that frame, the frame that is trying to extrapolate, and construct a small DFT cell contains the local atomic information. This has to be as small as possible and maintain the periodic boundary condition, because the DFT is a plane wave calculation, so we need to maintain the periodic boundary condition. We do the DFT on this small crack configuration and add the data back to the database, retrain the model, and repeat this process until there's no extrapolation detected. And this is the automated algorithm. So then we apply this algorithm to two crack systems shown here. So this is also the predicted error plotted as a function of a stress intensity factor. And this iter means the iteration of the active learning iterations. And this is the crack plane, and this is crack front. So we trained the system on these two cracks, active learning on this two crack system, and tested on this two crack system. We can see that in 4 iterations, the average error goes down and converge to less than 8 MeV. Okay. Here the video shows that during the entire cleavage process, we don't see any atoms with error above 8 MeV per atom. So we predict the fracture mechanisms for all for the 4 crack system shown here. They all show cleavage taking place on the original plane. We further calculate the universal bending energy, and by taking the derivative, get to the normal stress, the cohesive law of the 100 plane and the 110 plane. And it's 110 plane and 110 plane. And we found that the stress required to open these two planes are close to each other, so we don't observe any crack deviation actually. So, but in experiment actually, on this crack plane, the crack deviates to 100 plane. But that is, we conclude that is due to the dislocation, the background dislocation plasticity. And we predict the critical K for under different temperatures from 0K to room temperature, and the strain rates is 10 to the power of 9. And this the Kg, the solid line here is the Griffiths criterion, and the KIE is the rest criterion for the crack tip to emit a dislocation. And we can see that also for at those temperature ranges under the high strain rates, only cleavage take place. For the 0K to 1K, there is a slightly drop. This is due to the complexity of the gap, because the potential energy surface is a bit rough with a slightly thermal fluctuation smears out the entire potential energy surface. And as long as the cleavage takes place, the KIC is temperature independent, and it shows some lattice trapping effects because this compared to in atomistic simulation, it's expected to be the same as Griffith's prediction as long as the mechanism is it's cleavage, but it shows some lattice trapping effects due to the discreteness of the lattice. Our work also has an implication on hydrogen embrittlement, because recently we get this mechanism proposed by Giessen and the hydrogen-induced fast fracture mechanism, which is based on the assumption that BCC to HCP phase transition will occur ahead of the crack tip. Yeah, in our simulation we didn't observe anything. So maybe yeah, the HIFF, because this use of phenomenological interatomic potential, we are not sure that this is to be to conclude, we developed an active learning framework. This framework can be generalized to other machine learning potentials, other materials as well. And we obtain a quantum accurate gap for iron. And we observe that cleavage is a controlling mechanism under low temperature and high loading rates for magnetic iron. The next step would be to predict a finite temperature behavior through Arrhenius law and calculate the energy barrier for different mechanisms by not last band theory method. And we also want to, because the experiment shows that the fracture toughness of ferromagnetic iron shows a semi-brittle behavior, which means that the experimental predicted PSE is around 10, and we want to predict that, but this can only be achieved by considering the background dislocations. So the next step is also considering the dislocation plasticity and transfer the information that we get from atomistics to continue to the discrete dislocation scale. That is all. Thanks very much.
Thank you, Lev, for sticking to the time we have. Unless Larissa shows up or Ekaterina, we have time for a couple of questions.
Thank you very much. That was a very nice presentation. Can you show again, I think slide 7, where you have the active learning framework?
Yes.
Because I don't think I actually completely understand what's going on.
Yeah.
Because you specifically when you go, well, I can understand you detect an extrapolation.
Yeah.
And then you want to do the DFT calculation. But what kind of input from your MD simulation now goes into the DFT?
The configuration.
Yeah, but I would think so. But what exactly as
so
this configuration goes into the DFT? Is that
yeah.
just sort of like the displacement at the top and bottom boundary? Or?
No, it's actually this crack tip, because this color map is the gap predicted error is a rainbow, so red is the largest error. So you want the DFT to calculate the atom with the largest error, and you also want to construct a DFT cell that is as periodic as possible, as small as possible. So we came up with this idea to use extract the tip, the very tip of the configuration, and copy it, flip it, and construct, merge them together to get this. So this could maintain the periodic along this direction at least, and with this direction there is a surface.
And now how do you exactly load it? So because I guess the positions of these atoms exactly at the crack lip you want the lab free, right?
Yeah.
You want the DFT to compute it. So what is now exactly the boundary condition that you apply to the DFT?
It's periodic boundary conditions.
Yeah, so the top and bottom phase are basically, oh yes,
yeah,
periodic. Yeah, okay.
It's periodic. So in this figure you can see it's actually, you flip this one and merge it with this one, so you don't need to consider this as periodic, right? It's seamless. There is no spacious surface.
And then you just let it relax, basically. From that configuration, you let it
no,
the DFT go.
The DFT is self-consistent ground state calculation. It's not without relax, because you want to calculate the energy of this configuration. So exactly the configuration that is trying to extrapolate. You don't relax it. If you relax it, it's going to be different from the configuration that you want to calculate. So the gap doesn't know at this point, the potential doesn't know what to do with this configuration. It gets confused. It's trying to extrapolate, but you get the index of extrapolation. So you calculate it. You calculate this configuration and give it back to the potential to tell the potential, hey, this is what you want, and he knows what to do in the next iteration.
Okay. I'm still not exactly sure how you apply boundary conditions to the DFT, but at least a general framework.
Yeah, it's periodic. So it's just this cell with the box.
It's only top bottom periodic, right? Not right left.
Right left, you also need to apply the boundary conditions, but it will have a surface around here if you copy this thing. So the boundary conditions of DFT code is, if you don't set it, it's always it's always periodic. So here, so you would have a surface here, but the benefits of the machine learning potential is that you have a localization assumption, which means this atom is only assumed to interact with the atom that has within the cutoff radius. So you want the information of this atom. So this atom.
And so why didn't you take this configuration, the double configuration here, and flip it also like horizontally?
Yeah, that is a good question because this is already hundreds of atoms. It's already difficult to deal with DFT. If you add more, it's not easy to.
Thank you.
We're going to take one question, so maybe over there.
So I just wondered as well. So at the end of the tip graph,
Yeah.
are you using molecular dynamics or density function theory?
So here we use molecular
No,
dynamics.
the second picture.
This one?
Yeah.
No, this is just we take this frame out and zoom in.
Okay, it was the first picture using molecular dynamics simulations.
Yeah.
On the first picture. First picture, molecular dynamics.
Molecular dynamics.
You need to know like some potentials, some forces.
Yeah.
So from classical, fraction mechanics, there should be infinite stresses.
Yeah.
So kind of like which stresses, which potential are you using for molecular dynamics there?
So I use the gap. The aim of this framework is to develop the interatomic potential actually. So yeah, this one. I use the Gaussian approximation potential. It's called gap. So this one. We basically the work is to develop. To enable this potential to predict fracture. Yeah.
So that's some special potentials they invented already for like the corrective?
Yeah.
Okay.
Yeah. Then yeah, we can see the influence we can see the.
Well, I think we can
Yeah.
probably move to the next one.
Yeah.
Thanks a lot for your talk. Very interesting.